Okay, you made it through the first module of the Introduction to Java Programming course. So now you know a bunch of terms and how Java fits into the object-oriented landscape. You know that a class is the fundamental building block of everything in object-oriented programming, and classes are made up of two main components, the data members and the behavior. The data members are the attributes. The attributes store the data and represent the state of an object. The behavior is represented by methods. Methods are the subroutines. They're the functions that actually perform actions for the object. So what is an object? An object is nothing more than an instance of a class. So if I have a robot that has 4 motor controllers that are all, let's say the Talon SRX motor controllers, that means I have 4 instances of the Talon SRX. Each one of those instances is a separate object, meaning it has its own state. Each one of the 4 motor controllers can be running at a different speed. Each one of the 4 motor controllers has different voltage and different current applied. But they're all part of the same class. The Talon SRX class defines the contract that that motor controller will perform. It means it has to have certain methods and certain behaviors, and it will maintain certain attributes. You know that all objects exhibit 4 principles. There's encapsulation, abstraction, inheritance, and polymorphism. Encapsulation is information hiding. Abstraction is implementation hiding, so slightly different. Inheritance defines a relationship between 2 objects in an inheritance hierarchy, specifically an is-a relationship. And there's 2 other kinds of relationships I should mention. The has-a relationship can be either composition or aggregation, and those either define an ownership relationship in the case of composition or a uses relationship in the case of aggregation. And lastly, the last of the 4 principles of object-oriented programming is polymorphism. And a polymorphic type is one where the actual behavior implemented is determined by the object that is instantiated. So let's move on to some history of Java. Java is one of the newer languages in the landscape of object-oriented programming. It was created initially in 1990, but it wasn't publicly released until 1995. Sun Microsystems started working on it, and Oracle has purchased Sun Microsystems. So now if you want information on it, you go to oracle.com. Originally, Java was going to be a combination of Mesa and C. And then as it evolved, they decided to take it in the direction of being an extension to the C++ language. Finally, as they continued to evolve, it became its own language. But because of that hierarchy, it is strongly influenced by C++. So just like C++, it's a strongly typed language, and we'll get into that later on. Unlike C++, which compiles into native machine language of the computer chip that it's going to be run on, Java compiles into bytecode. Bytecode is an abstract representation of machine language for an arbitrary CPU. That means that in order to run a Java program, the bytecode has to then be translated into the actual machine language for the processor. That actually happens by the Java virtual machine. A long time ago, Java virtual machines used to interpret the bytecode, instruction by instruction as it went, and that was very slow and tedious. Nowadays, every Java virtual machine recompiles the bytecode into machine language at runtime, so you get a much bigger performance bang by doing the recompiling than you do by interpreting line by line. So what are the major features of Java? One of the big advantages of compiling into bytecode is portability. So once you compile into bytecode, you can run your program on many different platforms. Java has standardized primitive types in the bytecode. So when you compile it into bytecode, all of your primitive types are the same size no matter what platform you run on. That is not the case in C and C++. So that's a fairly notable distinction for Java. Another feature is the standardized features. Java comes out of the box with threading libraries, networking libraries, and it has security built into the language. It performs bounds checking on arrays, which is a huge source of errors in C and C++. So that's an advantage of Java. One of the reasons that's not in C++ is because it slows the language down. And back in the days that C was being developed, we're talking about the 1960s, computers were pretty slow. So any little trick you could use to squeeze a little bit more performance out of the computer was generally taken. By the time Java came along in the 1990s, computers were much, much faster, and it was deemed well worth the risk to sacrifice a little bit of speed for a little bit of security, or in some cases a lot of security. Java also has a very simple memory model, and I'm going to foot stomp this. We're going to go over this over and over again. Remember, in the Introduction to Java Programming Module 1, I mentioned unallocated memory is called the heap. All objects in Java are allocated on the heap. So what's an object? An object is the instantiation of a class. So every time you declare a class and instantiate it, it gets put on the heap. So we have to remember that. That memory allocation is not complemented by memory deallocation. Java has garbage collection, which means the Java virtual machine keeps track of all the references to all the objects that have been instantiated, and it automatically deletes the ones that are no longer referenced. So again, that's another feature of security, because memory management is one of the biggest sources of errors in C and C++. So again, Java has sacrificed a little bit of speed for that extra security. This is another foot stomp. Everything in Java is a class, and programs are nothing more than a collection of classes. Some other languages have different constructs. They may have functions, they may have macros. There's none of those in Java. When Sun Microsystems created Java as its own language, they simplified a lot of what the previous languages had come before. Every class in Java has a single file whose name is always the name of the class with a .java extension. So if I create a class called robot, the source code for that class will be robot.java. Once you compile that class, you create the bytecode representation of it, and the bytecode will have the same base name as the class, but it'll have a .class extension. So my robot class will be robot.class. Oftentimes, a whole family of related classes will get bundled into an archive file called a jar. Jar is nothing more than a Java archive. It's an acronym. Java has a few specialized types of classes. There's interfaces, there's enumerations, which are declared as enum. Enum is an abbreviation for enumeration, but they're still classes. Everything in Java is a class. So now we're going to go over some of the basics of the Java programming language. Every Java class starts out with a package. A package is a name that defines a group of related types. Remember, a type is a class because everything in Java is a class. And by putting it in a package, you're defining a namespace which defines a scope. So we'll get into that a little bit later. But in short, it allows you to have multiple classes with the same name. For example, the Java library that we use for FRC has a class called timer, but the Java utilities that come with the language also have a class called timer. We can do that because they're placed in different packages, which means they're in a different namespace. They have a different scope. So there's a java.util.timer, and there's a wpi.libj.something or another .timer. So those are in two different scopes. So Java puts its language types in standard packages, such as java.lang, java.io, and system. Every time you want to print a message to the console, you're going to use the command system.out.println. System is the package, .out is a subpackage within it, and then println is the actual name of the class. Every Java source file starts with the package line, and you must declare every external identifier with an import line. So what's an external identifier? That's another class. So if my robot class is going to have a Talon SRX motor controller, I have to import the Talon SRX. And the reason for that is you have to tell the compiler which scope that class is going to come from. You have to define where you're getting it from, because like I just mentioned, there could be more than one class with the same name. Access specifiers. I touched on this last module when we were talking about encapsulation. Encapsulation is information hiding. What is information? That's the state. Those are the attributes. How do we hide an attribute? We have to give it an access specifier that tells the compiler what blocks of code are allowed to access your attribute. So to make it private, that means access is only permitted within the current class. And if you do that, the only way anyone can get at your private attributes is to go through an accessor method or a mutator method. Those methods will be public. Public means they can be accessed from any scope, anywhere in any Java class. There's two other access specifiers. Protected, which means you can be accessed from the current class's scope and any of its subclasses. What's a subclass? That's part of inheritance. If you have a base class that's designed to be derived from, you could make some of your data members protected, which means the derived class would still be able to access the data member directly. The last one is probably used least of the four. That's the package scope. That allows access from the current package, but not from any other package. And it comes in handy for some things like unit tests, but it's used a lot less frequently than the other three. You'll use public and private the most often. When in doubt, make something private if it's an attribute. When in doubt, for a method, make it public. And we'll go into that as we get into later modules where we talk about the actual design of classes. So here's a real simple class structure. This class is named MyRobot. So we can see right here the class name is MyRobot, and it is a class. And it is public. So the MyRobot class is public. You'll get used to reading some of these declarations from right to left. The very first line of my class file would be the package, org.first.frc.robot. Packages tend to be your internet domain name in reverse order. So if my name is phantommentalist.com, which is the domain name for Team 2028, the Phantom Mentalists, the package would be com.phantommentalists. So in this case, the internet domain is robot.frc.first.org, and the package is that in reverse, and incidentally, all lowercase. So org.first.frc.robot.myrobot would be the scope that this class lives in. That is where it's found. That is its namespace. You'll also notice something I touched on earlier when we're looking at code samples. The curly braces will delineate the beginning of the class declaration and the end of the class declaration. So between these curly braces is all the class body. What makes up the body? That's made up of the methods and the attributes of the class. So variables. What is a variable? A variable is a means of holding data. Variables can be defined both in a class or in a method. If a variable is located inside of a method, it's considered a local variable that temporarily stores data while the method executes, which means that the memory allocated to store that variable is put on the call stack. Remember, last module we talked about the call stack as the most commonly used reserved section of memory. When the method invocation finishes, the stack frame in the call stack is released and all the local variables go away. They're gone. So nothing permanent is stored in local variables. Variables defined in a class are called attributes, and they collectively define an object state. And attributes will exist as long as that object, which is an instance of a class, exists. When the object is deallocated by garbage collection, the variables within the class are also freed up. Variables can be two different types, or can fall into two broad categories: primitive types or object references. Primitive types are the built-in types that the language comes with. Object references are just that. They are references to where the object lives in the heap. When we instantiate a class, we create an object, and all objects are stored on the heap. That's part of the simple memory model in Java. So The address of where on the heap the object is stored is called the reference to that object, and that's what gets stored in the variable, in the class, or in the method. So how do we declare a variable? You've already seen some hints of that. All variables, whether they're class attributes, local variables, or method parameters, are declared the exact same way. The type, a space, and the name. The type has to be a primitive type or a declared class. What do I mean by declared? You have to declare every external identifier with an import statement, which means within the class that's making the declaration of the variable, you have to import the type so that the compiler knows which kind of object you're talking about. The name of a variable can be any legal identifier. To make it simple, pretty much it's always a sequence of letters. Every now and then you'll see letters and digits. The language actually allows $signs and underscores, but those are reserved for certain special meanings, so they're not generally used by programmers. Names of variables are case sensitive, and one of the last modules in this Introduction to Java Programming, I'm going to go over the industry standard naming convention. What I would suggest is just because the language allows a legal identifier to be any sequence of letters and digits, don't literally follow that. Follow the common convention. It'll make your code a lot easier to read and a lot easier to maintain. The last thing that you want to have happen in the middle of first robotics competition, you're in the pits, you're trying to make a change to adapt a robot for some change due to a failure or some new capability, is to not understand your own code because you were creative and didn't follow the convention. It really does make a difference. So let's look at some example variable declarations. This first one, I, is an integer. Int is one of the primitive types in the Java language. So we read from right to left. I is initialized to 0. In Java, all variables are initialized. There's no such thing as an uninitialized variable, which is another security feature that's built into the language. It takes care of a lot of errors that tended to crop up in other languages. This next line, J is an integer, and it's initialized to 7. So this equal sign is an assignment. So J is an integer assigned the value 7. This next line, first name, is a string. Strings get initialized to an empty string, which means it contains no characters. The next line looks a little different. P is a double. I is a double, and D is a double. So we're actually declaring 3 variables on one line. The next line, radius, is a float with the access specifier private. So that would probably be a class variable, a class attribute. This next one has a lot more on it. Can ID is the name. Remember I said variables can include the number, the underscore, and this is one of those cases where we use it. In Java, one of the conventions is constant values in a class are always named all uppercase with underscores between the words. Can ID is an integer which is final and static and public and initialized to the value 14. So we'll get into what static and final mean a little bit later. Here's a non-primitive type. Launch Motor 2 is a CAN Jaguar, which is public. CAN Jaguar is one of the classes that FRC gives you in the API that instantiates a motor controller, specifically a Jaguar motor controller, connected over the CAN bus. CAN is an acronym for Control Area Network. Lastly, Engage Solenoid is a solenoid, which is public. Solenoid is another one of those classes that FRC gives you in the API for the Java programming. So what are the primitive types? I mentioned primitive types are the types that come built into the language. Java has them. There's only 8 of them, so it's pretty easy to keep track of. The first one is Boolean. Boolean can hold only 2 values, true or false. I should mention what I mean by this purple coloring. Just like the blue coloring is a foot stomper. That's something you're going to see again, so pay attention. Purple means it's a reserved word in Java, which means you cannot use these words to mean anything but what the Java language has declared they mean. So Boolean, true, and false are all examples of reserved words, as are the access specifiers. public, private, package, and protected. Char can hold one character. That's a 16-bit Unicode value. Byte is an 8-bit signed number. So that means you have 7 bits for the number and 1 bit for the sign, either positive or negative, which gives you a value of between -128 and +127, inclusive. Short is a 16-bit signed number. That means it has a value range between -32,768 and +32,767, inclusive. Int is an integer. It's a 32-bit signed number, so it has a value between -2.147 billion and +2.147 billion. Long is also an integer type, but it's a 64-bit signed number. So it has a number between -9 point something and +9 point. So pretty much a humongously big number. All of these, byte, short, int, and long, are integer numbers. That means they have no decimal point. They only have values of whole numbers. There's two ways to represent real numbers in Java, float and double. Float is a single precision IEEE 754 base floating point number. Double, as the name implies, is a double precision IEEE 754 base floating point number. Just by coincidence, the entire Java API that you're given by FRC tends to use double for all of its parameters, which means you'll tend to use double for all of your values as well to cut down on the number of conversions between float and double. But in real life, you tend to use float and double about equal numbers. So here's a caveat about real numbers. There's no such thing. Computers, at least modern computers, are digital. That means they run on a binary system. And real numbers are not binary. So float and double are only approximations of real numbers, which means certain values have no exact representation. Unfortunately for us, in the FRC world, a lot of the values we use most often actually have no representation. So what do I mean by that? We know that there's 12 inches in a foot, which means 1 inch is 0.083333 repeating feet. So if I take 0.083333 times 12, I don't get 1. I get 0.999996 feet. That's not an exact representation. Another one, there is no 1/10. So 1/10 in decimal is 0.100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 I don't get 0.3 plus 0.9, I don't get 0.9. I get 0.89999999999. What that means is if you compare real numbers with an exact comparison, it won't work the way you think it does. So don't do that. Whenever you want to compare, use a range. A range would be greater than or less than. So for example, if you have a deadband in your joystick because the joystick tends to drift, you don't want to say if joystick.getX equals 0. You want to say if joystick.getX is greater than -0.02 and joystick.getX is less than 0.02. So that gives us a 4% deadband around 0 rather than comparing for exactly the value 0. And again, that word if is in purple, which means that's a reserved word. We'll get into what the rest of the syntax on this if statement means a little bit later. So here we have an example of a class called left. The class is delineated by the open curly brace and this closed curly brace down at the bottom. Within the class, we have a method called main. Main returns void, is static, and is public. We'll talk about the void and static a little bit later. Main takes a parameter named args, which is an array of type string. These open and closed square brackets denote an array. An array means it has multiple values. There's more than one string that make up args. It then has a variable called first, which is a Boolean, which is initialized to the value true. Then, inside this for loop, it has another variable I, which is an integer, which is initialized to 0. So storage for all of those variables has to be created on the stack frame for this method main. So here we have the stack frame for main. It contains memory for the variable first, which in this example has false. It has memory storage for the variable I, which in this case has 9, and it has memory storage for a number of strings. And we'll get into what the strings look like a little bit later, so I'm intentionally leaving them blank. So it has storage for one parameter, args, and 2 local variables, in addition to the address of where we return to when main exits. So if we go through this for loop, just like in C, which was the example I gave in the module 1, just like in C, we're declaring a variable I, initializing it to 0. This first stanza before the first semicolon is the initialization. So that's our loop initialization. The second stanza is the comparison. So as long as I is less than 10, we stay in the loop. And the third stanza is the incrementer. And in this case, we're incrementing I. The plus plus is an increment operator. So while I is less than 10, we stay in the loop. What is the loop delineated by? The loop is delineated by this open curly brace and this open or closed curly brace down here. So that's the body of our loop. Inside our loop, we have if not first. That exclamation point is the operator not. So if not first, we print out a comma. Otherwise, we print out the variable I and set first to false. So the first time through, I is 0, first is true. When first is true, we skip over the body, the statement inside the body of the if statement. Go right here, we print out 0, set this to false. We come back up, increment I to 1, I is less than 10. Now first is false, so we print out comma, space. Then we print out 1. Set this to false. Increment I is now 2. First is false, so we print out comma, space. We print out 2. Increment I to 3. 3 is less than 10. Comma, space, 3. So on and so on and so on and so on. Eventually we increment I to 10. Now I is not less than 10, so we skip all the way down to here. Notice that this is println. Println means print a new line. Print out the statement and put a new line at the end of our print. All the others were print without a new line. So the result of this subroutine, it's going to print out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then enter. It's going to return back to the leftmost position on the console. So it prints out the numbers 0 through 9. So how about non-primitive types? Non-primitive types store the location of an object on the heap. So that's the location in memory, that unallocated memory or unreserved memory that has now been allocated by the creation of the object. They're initialized to null. Remember in Java, every single variable is initialized to a value. So object references are initialized to null. Null is a reserved word. You can't use that yourself. Well, let me rephrase that. When you use it, it means the value object reference not pointing to any object. Objects have to be allocated before you can use them. So to allocate it, you use operator new. Forgetting to do this causes a null pointer exception, which is probably the single most common error in Java. You don't have to do any deallocation. Java uses garbage collection. So garbage collection frees up the resources when the last reference to an object is deleted. And you cannot differentiate between aggregation and composition by declaration. That's problematic. That means you need documentation, or you need very tedious study of methods to understand what kind of composition is represented. Personally, I think documentation is the way to go, and we'll get to that in, I think, Module 7, possibly Module 8. So don't worry, it's coming up. So let's look at another example. This is our class left. Left has a single method named main, which is a method that returns void, is static, and public. It has one argument, args, which is an array of string, just like before. It also now has an object reference variable, PL. PL is of type place. Place is a new class, which I've declared right down here. And we're initializing it with the operator new place. So what that does, when we invoke main, we create a stack frame. The stack frame has storage for two things in it. Our object reference PL. It still has args. I didn't show args for simplicity, but it's still there. You know it, you love it, you'll still cherish it in your heart. But PL is the interesting one for this example. PL is of type place, so operator new is going to go out on the heap and it's going to create an instance of the class place named PL. If we look at that class, it has longitude, which is a double, which is public. It has latitude, which is a double, which is public. And then in main, we're going to invoke. This is a period. The period is known as dot. It is the dot operator. So we're going to invoke the initialize member of place. The dot means member of. So remember, every class creates a scope. So the dot in this case is the scope of. So we're invoking the initialize member of PL. That is a class or a method down here called initialize. It sets longitude, which is the local class variable for PL, to 37.0342934. And it sets latitude to negative 76.3174313. So if we now go and look in the heap, once we invoke the initialize member of PL, those two variables have now been given those two values. So that's how object references work. This blue arrow shows that it's holding the location of where the object really lives. Why is that important? That's important because we have no idea how big an object could be. Suppose my object was going to be the Encyclopedia Britannica. That could be gigabytes worth of data, but the object reference is always the same size. It's only the location of where the object is stored. So I just spent a lot of time talking about methods in classes. So what is a method? A method is an operation that performs actions. It is the behavior of a class. They change the state of an object and contain Java statements. Methods can optionally return a value. We just saw that with our method main. Methods that do not return a value are called void. All other methods, other than a constructor, which I'll talk about in a second, must have a return statement. So what does a return value mean? A return value means we're going to push one more value on the stack to return something back to the method that called us. Methods can also take parameters. All parameters are passed by value. So what does that mean to pass by value? That means we're going to take the value and copy it into the method stack frame. But what if it's an object reference? The value of an object reference is the location on the stack where it is stored. So we're not copying the actual object, we're copying the location of where it's stored on the heap. So this is in bold all caps. We do not copy the actual object. Java will decide which method to invoke by the method's signature. So a signature is a combination of the method's name and its parameter types, but not the names of the parameters, only the types of the parameters. Also, note I did not say the return value. It only looks at the method's name and the parameter types. So here's another example. This is class 1. Class 1, I'm now returning to what we had before. The purple means it's a reserved word. Class is a reserved word. Main is a method that returns void. That means it does not return anything, which is static, and its access specifier is public. It has an argument args, which is an array of string. It has a p local variable, which is a pair that's initialized to a new pair that we just allocated. So again, we still have args in here. I'm not showing it for simplicity. P is initialized to contain the location of where pair is stored on the heap. Pair has a first and a second. So here's class pair down here. It has first, which is an integer, second, which is an integer. Those are initialized to 0 automatically for us by the compiler. Now we're going to invoke the method count. Count is going to pass p as a parameter to that method. So what actually happens? Now we're down in the method count. We've created a new stack frame on the call stack for count. Count has its own local variable that is a pair. That's different than the p here. Keep in mind, the p in the stack frame for main is in that stack frame, and the p that's in the scope of this method count is in that method's stack frame. So this is in a different scope. The scope is delineated by these curly braces. So now we have made a copy of the location of this p and passed it by value into the parameter in count. So they both point to the same object reference in memory, the same location on the heap, but they are different object references. That's what I mean by pass by value. So there's one special kind of method that you have to know about. That's a constructor. So that's blue. Blue means pay attention. I'm going to foot stomp that. That's an important, that's a big deal. A constructor builds a new object. Java will guarantee the constructor is called whenever a new object is created. When are objects created? When you use operator new. So it's automatically called for you, and its job is to initialize all of the data members in the class. Every single class has a constructor. Java guarantees it. It will create one for you if you do not. So in that previous class pair, there was no declared constructor, so Java went ahead and created one for me, which initialized first and second to 0. You can overload a constructor. So I'm going to get into overloading in just a second. What is an overload? An overload is two methods with the same name but different signatures. So we'll get to that on the very next slide. A default constructor is a constructor that does not take any parameters, and its job is to initialize all the data members of a class, all the attributes of a class. There's also a copy constructor, which takes a reference to an object of the same type, and its purpose is to perform a deep copy of every attribute. Copy constructors actually come from C++. They don't actually come from Java, but they tend to be pretty handy, and you will tend to see them in certain classes. So here's the important detail. A constructor's name is the same name as the class it comes in. So the constructor for class pair is called pair. And remember I said every method returns a value or is void except for the constructor. Constructors do not return a value, not even void. So I said overloading in this last slide. So overloading occurs when you have more than one method with the same name but a different signature. The signature is the name plus the parameter types. So if it has a different signature, that means it must have different parameter types. It's most commonly used with constructors. So you might have a default constructor that initializes everything to 0, and you might have an overloaded constructor that initializes values to something else. It's useful to provide several variants of the same behavior. So here's a couple examples. Let me get my mouse cursor ready. We're going to invoke the drive member of robot, and we're going to pass it a steering wheel and a throttle. That'll give us a car drive type behavior. Or we can invoke the drive member of robot and pass it joystick 1 and joystick 2, which could be your left joystick and right joystick, and that'll implement a tank drive. So the compiler knows which one of these two methods to invoke by the types of the parameters, because they both have the same name. So that's an example of where you might use overloading that's pretty handy, and it actually does get used quite a bit. So I promised you we would go over static and final. So static attributes, remember an attribute is a variable inside a class, have exactly one copy for every instance of that class. So a lot of times they're used for constant values, but they don't have to be. So if you create a static attribute, no matter how many objects you instantiate, you only have memory storage for one of those variables. You've already seen static methods. Let me back up a little bit. A method in Java usually has an implied parameter, which is an object reference to itself, to its own instance on the heap. That implied parameter is a reserved word that's called this. If you declare a method as static, that means it does not have that implied parameter. It has no reference to any instance of its own type, which means it cannot access any attributes that are declared within the scope of the class. It can still perform functions, and we're going to see that a little bit later when we get into some actual FRC examples. It is very powerful, but it's not as common. The one place it is common is with main. You saw the method main was declared static. That means it could not access any of the attributes declared in the class that it came from. If it wants to access an attribute of a class, it has to create an instance of that class on the heap using local variables. Final. Final means a couple different things. If a class is final, it means it cannot be subclassed, which means you cannot derive from it. It is not part of any further subclass inheritance hierarchies. Methods that are final cannot be overridden. I have not spoken about overriding methods yet, so we'll come to that later. So it's not bolded and blue yet, but it will be. Attributes that are declared final can only be assigned a value when created. That makes them a constant value. That's used a lot for things that never change. One of the things that happens a lot in FRC robots is certain properties are decided by programming the firmware of a motor controller or by physically running wires to ports on the RoboRio. And we'll get into that into the next class, the FRC class, which goes over the API in detail. So for things like that that never change, we'll make them constants. And the way we make things constants in Java is by declaring the attribute final. The interesting thing is that if the final attribute is not a primitive type, which means it's an object reference, you can still change the state of the object, but you cannot change which object it refers to. So just keep that in mind. That's one of those caveats that you've got to keep in mind when you're doing your programming. So here's another simple class. This class is named simple. So now we've gone over pretty much everything in it. So we read this right to left. Simple is a class which is public. That's its access specifier. It's delineated by these curly braces. It has one attribute which is named number of type integer. So number is an integer. It has a default constructor. The constructor always has the same name as the class. So our constructor is named simple and our class is named simple. That's how I know it's a constructor. And it does not have any return value whatsoever, not even void. This particular constructor happens to be public, which is the norm. You can make them private or protected, but that's less common. The job of a constructor is to initialize all of its attributes. So we're making doubly sure that number is initialized to 0. Where's number? Remember, non-static methods always have an implied parameter to an object reference of itself. So this is saying number in the scope of myself. So this number is referring to the variable number, which is an attribute in the scope of the class. We could also declare local variables. This particular simple constructor doesn't declare any. So that's it for this module. Hopefully, you're starting to piece together some of the examples that you saw both in the module 0 as well as this module, the Introduction to Java Programming. Hopefully, you've learned enough to be excited to move on to the next module, which is going to review Java statements. That's it for now.